Yes.
But it's above coupling. Can you explain that?
We didn't have any theory in that paper. I know you're a theorist, so we could use some help. we look into many theory paper. They're basically it's the where the Fermi surface is, which orbital it finishes at, and whether it has a spin orbital, a strong spin orbital term at that orbital is what mattered. That's only our speculated explanation.
Okay, thank you.
Any other comments? So I think when you make devices, spintronic devices, there are many things can vary, right? So here we're trying to take out one variable for you to say, this is where you look for logic DMI interactions. Other variability may come from the fabrication process. So I should also say empirically, these measurements are actually very fast. This thermal measurement only take 2 minutes. It was very fast. Well-behaved mode. When you have this very well-defined mode, it's actually easier to measure them in frequency domain. So we were able to measure these film or measure their spatial dependence rather quickly. So this is another thing that we've gotten better over the years. Okay. Other questions? Questions? Okay, if not, I feel like a real break. I don't know about you, but I can go on. Should we just go on? Okay, or you can, one thing I always imagine people should do at conferences is stand up and do, exercise, at your seat for like 3 minutes, right? So I exercise regularly because I find that was needed to keep up my energy levels. But maybe the chair can let me know if I should give you a real break or not. If nobody screams, I'm gonna continue. You all look good, so I'm amazed you're still awake at this hour. Anyhow, so this is a collaboration where we are able to characterize the DMI, and then we were able to collaborate with the ND sensing group that really try to measure the texture of that spin texture. So take-home message for this part. So you can, we really need to understand interfacial interactions. They're critical for designing exotic spin texture skyrmia in this particular cases. We think you can actually quantify important interfacial interactions like DMI using by measuring Magnon dispersion. So you can quantify such DMI interaction between different heavy metal ferromagnetic bilayers, or even in this, when we did that work on iridium manganese was one of the first example of DMI AFM-FM interface. That would at the time actually enable the first demonstration of skyrmia at zero applied field and at room temperature. So that was a little contribution to something that's useful. So the second topic I was going to talk about is related to spin electronics. Okay? And the goal is to harvesting some waste heat in spintronic devices to do something useful. But I was going to pause again, and before I go on to the next topic, and to see if you have more questions about what I just talked about, measuring DMI. Yes, please.
Actually, I have a question about the spin wave dispersion you showed just now.
Yeah.
So from the formula, we can see the first term is a parabolic shape, and the second term is a linear term.
Yeah.
So in your in the figure you shown at the right side, I think it's mostly parabolic shape.
Right.
So from the BOS measurement, we are mostly, I think, studying the parabolic term-like behavior. in a. So I want to know, is there any advantage which in the exchange-dominated region, for example, in this region the K vector is larger, so we want to use this BOS measurement to study. Why I ask this question is because maybe around 10 years ago there are many researchers study the low K vector region about the magnetostatic spin waves. But here, what we are measuring in BOS is exchange-dominated spin wave.
Right. So okay. So I think first of all, using light scattering, typically you would using that language I use, momentum conservation, right?
Yeah.
Photon carries very little momentum compared to the whole Brillouin zone. Typically, you would think you're only probing long wavelength spin waves using light scattering technique. But when you have, geometrically constricted structure, then you can actually pick up, that would influence your measurement. So, the fact that, the momentum in the perpendicular direction is not even conserved, right? It's absorbing this heavy metal. These metals are highly absorbing. So I'm not, I'm assuming the momentum conservation is only conserved in the in-plane direction. That's approximation. Okay. So, momentum conservation holds because of translational symmetry. In a lossy material, momentum conservation does not strictly hold. Okay. So this, in many ways, are approximation that seem to work. Okay. So and these spin waves, what is their wavelength? The probe spin wave typically is actually related to the size of the structure I'm measuring. So because the physical structure also basically break translational symmetry. So the momentum conservation is only approximately conserved in that whole process. Okay, so I think I had long conversation with my group about this. Nobody wants to give up momentum conservation, but you have to understand it's actually a result of a translational symmetry. When you have a constrained geometry, where you have losses, over the length scale of 10 nanometer, the momentum conservation is out. So this language is approximate. Okay. And then the wavelengths of the magnon I pick up oftentimes actually constrained by the geometry of the device I'm measuring. No longer by the photon momentum.
But after this momentum conservation, so we are probing actually a much larger wave vector than the magnons we are interested in maybe 10 years ago by using this optical method. I think maybe there are some advantage of the magnons we are probing in this high wave vector regions.
I would still call them low K compared to the Brillouin zone. They're still low K. They're still low K range. Okay. So the wave vector, if I were to calculate the wavelengths, they're 100 nanometer. So the 100 nanometer is in between the exchange region and dipolar region.
Oh, I see. Thank you.
Yes. Yeah.
The other method of estimating value of BMI is from the spin spiral.
Mm-hmm.
Has anyone ever benchmarked the accuracy of BLS estimation against the spin spiral, like real space imaging?
I'm not aware of that, but actually in as many measurement in material, people, just like damping measurement. When you use FMR to measure damping versus if I try to quote a damping using line width in Magnon measurement, the number don't match. The only thing you can hope for is if I say this film has lower damping than that film, I measure them with both technique. Hopefully they would typically agree, but the numbers really don't, right? So it's a very interesting problem for people who do measurement. How you're your measurement tool are probing certain aspect of that material, and sometimes very differently. Something it's actually hard to agree on who has the better measurement. I can go on forever on this, but I would say I'm not aware of any correlated magnitude. We couldn't even correlate the damping measurement using this type of light scattering with FMR, for example. We just couldn't reach the same number, no matter how we play with the parameters. But usually, if they say it's a low damping film, we measure a natural line with it in Magnon as well. Okay, any other questions? Okay, if not, I'm going to start the next topic. Spin colortronics basically has to do with a temperature gradient can drive Magnon motion, or spin wave motion. So it was launched by a serious paper where they find the so-called spin colortronic phenomena is very common. It may be also motivated by the thoughts. They have real applications. If you think about, how do we touch screen? How do we interact with the electronic devices? Maybe a temperature gradient can be used to drive a spin current. There were a lot of controversy following the early work, and I would say, the longitudinal spin seeback effect in insulator is most well established. I think we have some expert in the audience who spent far more time than I did on this particular problem. But what I wanted to do with you is to actually appreciate, think about how do we even define temperature? So, a lot of time, this spin color, so this spin seeback effect is in principle a non-equilibrium phenomenon. But as a person who spent a lot of time on measurement, I like to know, in an insulator, right, what is the energy carrier? Energy carrier is phonons and magnons, right? What is the spin carrier, spin current carrier? Is the magnon. So I like insulator for that reason, because it's simpler for me to think about from a quasi-particle point of view. So we started by asking the question, how do we even define local temperatures for phonon and magnon? Because a lot of time to explain this spin colortronic phenomena, you need to consider the interplay between magnon and phonons and their possible non-equilibrium locally. So how do you measure temperature? If you're looking at the old slide I gave you, I have a picture, a weird picture of measuring temperature of a baby. It's an old slide I made when I had my kids. I had to learn some new skills quickly. So that's why that picture is there as I took it out. So typically you measure temperature by taking a probe and have it reach equilibrium with the object you're trying to measure. So of course the most common way of measuring temperature is a resistance measurement. But the situation we have to deal with in spin colortronics is far more complex. So as a concept, temperature is only strictly defined for equilibrium system. And now we need to actually distinguish temperature for different excitations. I need to ask, is the electron, phonon, or magnon at the same temperature? So if you study these kind of non-equilibrium transport property, you often see what's called the 3 temperature model. You will assign the electron temperature, phonon temperature, magnon temperature. Those models are better than nothing, but they're really not very useful unless you can actually measure these temperatures independently. So then how do we measure their temperatures? So I need to be brief on this. So I would say you can measure temperature anytime you have a temperature-dependent quantities. So my temperature-dependent quantity here is basically the BLS spectrons. So this is a phonon spectron, and this is a magnon spectron, and measured on the YAG bulk crystals. Again, I bet there's a lot of fans and a lot of people who study YAG. Right? So, and the way I drive YG out of equilibrium is I actually heat them up using a separate laser. So I use a laser to heat up the sample, and then I use another laser to probe the phonon magnon mode. The reason I do that is because I can actually create a very large temperature gradient using a local laser heating. And this temperature scale, temperature gradient scale is relevant for those spin caloritronic measurement. That's one of the reasons. The second reason, a lot of time people cannot agree on how to characterize a temperature gradient in their film. So a laser heating is actually a remarkably simple way because you can calculate the temperature profile. Okay, so it's very easy for me to distinguish phonon and magnons because they have different frequencies, right? The phonon frequency is, in this particular case, a tens of gigahertz. The magnon frequency depends on the applied field, and of course, a shift with the applied field. So we can easily define phonon and magnon temperatures based on their spectrum. So the number here is temperature change from room temperature. So if I don't heat up my sample, I have a phonon spectrum that look like this. When I heat up my sample, the phonon spectrum has a very subtle shift. It's a little hard to see, but magnon has a very dramatic temperature shift. Okay? So what I'm trying to tell you is that using light scattering technique, I can measure these quasi-particles. I can characterize their temperature locally. Okay? So now I can actually define what's the temperature of the magnon, what's the temperature of the phonon, and I can see that I drive them out of equilibrium. Okay? So the conclusion is yes, you can drive phonon magnon out of equilibrium. And based on this comparing laser heating and stage heating, this is a magnon frequency shift. I use a model, I can actually precisely define the phonon temperature using COMSOL calculation. I can actually quantify the phonon population, and then I can use this to extract a magnon diffusion length. So this is early work, several years ago, but some time ago. But I thought this is a great example how I use light scattering to solve a very fundamental problem, thermometry problem. Thermometry associated with particular quasi-particles. Okay, so that's the second topic that I want to tell you. I'm done with this section as well. Any questions on this? So I know I was pretty fast going through the slide, but the basic idea is I calibrate the phonon and magnon temperature by doing a heater equilibrium measurement. So I heat up my sample, wait for equilibrium, then measure how the magnon frequency shift as a function of heating. I do the same for phonon, and then I create a spatial non-equilibrium, and I measure the magnon frequency again. Then I can actually characterize the magnon temperature that way, due to heating. Then I can compare the local phonon, local magnon temperature, and ask, are they out of equilibrium? Under what condition? So this allows me to do some basic, understanding of non-equilibrium phenomena in materials. So let me just briefly talk about the next one. So this has to do with a lot of relaxation process. Energy relaxation and the spin relaxations are different in magnetic insulators. So using the same idea, we were actually able to quantify spin current by measuring the local magnon population. So again, that's a hard thing to do. It's actually very difficult to quantify spin current in an insulator. A lot of time people put another metal on the top and they rely on some, what they imagine a magnon transfer from the magnetic layer to a heavy metal layer and measure the voltage in heavy metal layer. That is, to me, is difficult because you're counting on the interface is reliably repeated in different labs, and that's often not the case. Right? So here, using light, I can actually do a measurement of spin transport and energy transport in the insulator itself. So this is where light scatter really have an advantage, is to measure insulators. So I don't rely on any spin transfer to a heavy metal layers and quantify that way. Okay, so so in this work, we actually have to kind of deal with the concept of Magnon chemical potential. I don't know how many of you have heard of that, but it's highly controversial. Because anytime I define chemical potential, I'm assuming that's a conserved quantity. So it is not always obvious why that's the case. So I'm going to skip that topic entirely, and just to say, again, using this light probing method, I can quantify the local phonon temperature and local magnon temperature, and therefore I can trace the energy transport and the spin transport separately in the insulator. I'll just leave it to a take-home message, is we can develop temperature sensor for different quasi-particles. And then we can measure the phonon-magnon non-equilibrium. And finally, we can actually quantify different components in the spin current, either driven by a temperature gradient or chemical potential gradient. So it's really about quantifying spin current. So I'll leave it like that. I know I rushed through this topic already, but anything you can come up thinking or asking me, I'm happy to answer them now.
So yeah, a bit confused with the temperature of your magnons and phonons.
Yes.
So the procedure is that you have you're measuring the change in the frequency from your of your magnon by applying the temperature by heating your sample, but that temperature applied, the heat temperature of the sample, that's not the magnon temperature at that point, is it? Or is it like it?
Right, so I really rushed through it, but let me just repeat the basic step.
Yeah.
So what I'm trying to do is to find a new way to define magnon phonon temperature by looking their light scattering spectrum. So the first step is the calibration step. So this is the first step is to measure the phonon and magnon spectrum at room temperature. Then I put them in a heater stage. Then I can control the heater state temperature, wait for a long time so that the sample reaches the equilibrium with the heater stage. So I'm doing these calibration measurements all at under equilibrium condition. So the whole sample, either magnon or phonon, reaches equilibrium with the sample stage. So I measure under equilibrium position how the phonon spectrum and the magnon spectrum changes with temperature.
So that, for example, then the trace that's say at 43 Kelvin
is heated up 43 by the temperature sensor on the heater.
But then you take away the heat and then remeasure the trace? Yeah.
That's right. So this is my calibration step. So I'm calibrating thermometry for phonon and magnon by doing equilibrium measurement.
Mm-hmm.
So because I create this situation, I mount the tiny crystal on a big heater, get them to reach equilibrium, monitor how the spectrum change. Now to understand things like spin calorimetry, I need to create a spatial non-equilibrium. But it's also steady state. So what I then do is to take a laser to heat up the temperature, heat up the sample locally. So now I expect expect the temperature profile. My laser beam is always a Gaussian beam, right? Then the middle heats up the most. Then I have a non-equilibrium situation where the phonon and magnon would actually move away from the high temperature to low temperature. Then I ask the question, in this spatial non-equilibrium situation, is phonon magnon out of equilibrium?
Okay.
So that's the question I try to ask. Can I drive phonon magnon out of equilibrium? Because that was a very fundamental question to explain spin calorimetry phenomena.
Okay.
And this also, this is counterintuitive. If they're coupled weakly in a YAG sample that has very low damping, in fact, phonon and magnon couple very weakly. If they're coupled weakly, you can drive them out of equilibrium. If they're strongly coupled, they always reach local equilibrium too. So the fact I can drive them out of equilibrium is entirely consistent with the phonon and magnon in YAG couples very weakly. As a result, they can get out of equilibrium.
Okay.
So, in fact, when you're searching for low damping insulator, you want to look for a situation where phonon and magnon couple weakly. Otherwise, phonon would dissipate, with the cost of dissipation.
But so then that's the case only for this sort of would only work for a insulator, because then if you've got to conduct, if it's a metal, you have electrons as well, and then that means that it's...
Metal is so messy,
Yeah.
because electrons, it's a heavily damping mechanism for both energy and spin current.
Right. Okay. Yeah. Still probably going to be thinking about it for a while, but yeah, it's interesting. Thanks.
Yeah, thank you for that question, because I know I'm rushing through it, but I'm doing a calibration step by doing equilibrium measurement. Then I ask the question, can I find a situation where I have phonon magnon at different temperature? Because that's what you need, a critical thing you need to find a good material for spin caloritronic application. Okay, any other questions? I really like to applaud you for staying awake. I'm getting tired myself. But let me use the next 15 minutes. I promise I won't go over time, because we have a dinner reservation to go to, so we won't go over time. But I want to share a couple of things that are newer that my group has been doing the last couple of years. I'm drawn to new materials. One of the things that we started to work on is these van der Waals material. I have already acknowledged most of my research aren't too useful. This is one of those. So it's not very useful yet. Okay. But they're very compelling. So we've heard about tuning magnetic property using strain. These van der Waals materials, so first of all, how many of you have heard all the fuss about van der Waals material? Raise your hand. Yeah, only about less than half of you. So the van der Waals material is a class of material that have very strong in-plane bonding, but very weak bonding between the planes. Between each individual sheets, they're bonded by van der Waals material. Just most famous example is graphene. Okay, so of course we know graphene has already won the Nobel Prize. My prediction is this class of material is going to win another Nobel Prize. I don't know when, but there's really a lot of fascinating condensed matter physics that are being done in those systems. So actually even in the first paper published by the Nobel laureate, they show a very vast variety of material that can be isolated to a single layer thick. Not only they showed graphene, they show semiconductor, they show superconductor, and of course they're magnetic material that are van der Waals material as well. So because they can be easily still hard work for the student working on this, especially a lot of magnetic van der Waals material are not air stable, so people have to process them in a glove box. It's very uncomfortable to stand all day long with your arms sticking out in a glove box. But what's compelling about them is you can create exactly unit cell thick films. You can create maybe 2, 3, there's many layer thickness dependent property. Also what's interesting is you can actually create rotated structure that's called moire superlattice. And that it's actually turned out to be a great way to engineer topology as well. So this is really not the focus of the the short talk I want to give on this topic. But there are just many ways you can manipulate this material to create a superlattice, look for topological spin waves, and they have valley. I talk about valleytronics. There's also binary degrees of freedom associated with valley. And of course, they're very soft. Then you can tune their property using strain. And you can strain it so large that you can actually create a sizable pseudomagnetic field. So there's many things. There's a reason why physicists are obsessed with this material. But they're not going to be useful anytime soon. So you don't, if you're only interested in application, you can take a nap. Okay. Particularly, people are interested in this interplay between topology and magnetism. I just talked about these expanding van der Waals material. So they're also amazing for creating proximity field. So you can have these magnetic films that perfectly terminated, either ferromagnetic order or antiferromagnetic order. The proximity field is on the order of 10 Tesla. And you can use that 10 Tesla field to do many different things. And then in the topological material, there's all these exotic condensed matter phenomena predicted. Maybe the only thing that some of you will be interested in is some dissipationless chiral edge state. So then they also have a quantized magnetoelectric effect. So enough said. What is the material we started to looking at is a material that's one of the first known examples that's topological material, but also have an intrinsic magnetic order. So a lot of people were doping